Welcome to the final chapter of our Battery Materials Informatics series. After learning fundamentals, methods, and hands-on implementation, we'll now see how these techniques are applied in real industrial settings. We'll examine 5 case studies from leading companies and research institutions, showing how MI accelerates battery development and solves practical challenges. By the end of this chapter, you'll understand successful MI applications in industrial battery development. We'll cover 5 case studies: all-solid-state battery solid electrolyte discovery, Li-S battery sulfur cathode optimization, fast charging protocol development using reinforcement learning, cobalt-reduced NCM cathode design, and nil-ion battery material development. Each case shows the complete workflow from problem formulation through validation. One note before we begin: where we cite a specific publication, the results are that studies. Everywhere else, the compositions and performance numbers are illustrative worked examples assembled from published ranges, not measurements from a single named experiment. Our first case study addresses one of the most anticipated next-generation battery technologies: all-solid-state batteries. Toyota and other major automakers are racing to commercialize these batteries by 2027. The key challenge is discovering solid electrolyte materials with the right combination of ionic conductivity, stability, and processability. All solid-state batteries offer compelling advantages. High safety comes from eliminating flammable liquid electrolytes. Energy density can exceed 500 watt-hours per kilogram by enabling lithium metal anodes. Wide operating temperature range enables extreme environment operation. Developers target lifespans well beyond 10,000 cycles for stationary use, though that has not yet been shown in production cells. However, the solid electrolyte must achieve high ionic conductivity comparable to liquid electrolytes, while being chemically stable, mechanically processable, and cost-effective. 3 main solid electrolyte families are being developed. Sulfide-based materials achieve the highest conductivity but react with air moisture, complicating manufacturing. Oxide-based materials like LLZO garnet are more stable but offer lower conductivity. Polymer-based electrolytes are flexible and easy to process but have the lowest conductivity. Each system has trade-offs that MI can help optimize. The MI approach combines multiple techniques. First, we screen thousands of solid electrolyte candidates from the Materials Project database. Graph neural networks predict ionic conductivity from crystal structure. Bayesian optimization guides the search toward promising compositions. DFT calculations validate stability before synthesis. The training data combines experimental measurements with DFT calculations. Key descriptors include lithium vacancy concentration, lattice parameters, and activation energy for ion hopping. The implementation uses gradient boosting regression on engineered descriptors. Input features include lithium vacancy concentration, lattice volume, and activation energy. Bayesian optimization searches this descriptor space for maximum predicted conductivity. Low activation energy is particularly important for high room temperature conductivity. The optimization discovered a modified lithium phosphorus sulfide composition with chlorine doping. This material achieves excellent ionic conductivity. Experimental synthesis and measurement confirmed the predictions were accurate, with good agreement between predicted and measured values. Crucially, chlorine doping improved air stability. Interfacial resistance with lithium metal meets practical targets for device applications. Toyota aims to commercialize all solid-state batteries by 2027. Their projected performance is remarkable, driving range exceeding 1,000 kilometers per charge, over twice current EVs. Charging time targets 80% in 10 minutes, comparable to gasoline refueling. Techniques like the ones we've discussed are widely used in solid electrolyte research, though the details of any one company's internal pipeline are not public. Several other automakers have announced solid-state programs of their own, which underlines how much industrial weight is behind the technology. Our second case study tackles lithium-sulfur batteries, which promise the highest theoretical energy density of any rechargeable chemistry. While commercialization remains challenging, MI is helping solve the degradation mechanisms that have limited practical applications. Lithium-sulfur batteries offer a theoretical capacity of about 1,670 mAh per gram, roughly 6 times the theoretical capacity of lithium cobalt oxide. Theoretical energy density is exceptionally high. Sulfur is cheap, abundant, and environmentally benign. However, intermediate polysulfide species dissolve in the electrolyte and migrate to the anode in the shuttle effect. This causes significant capacity loss in early cycles with low coulombic efficiency. Practical batteries need thousands of cycles with high efficiency. The strategy focuses on designing carbon host materials that physically and chemically trap polysulfides. Molecular dynamics simulation, combined with machine learning, predicts how different carbon structures interact with polysulfide species. Transfer learning from lithium-ion cathode research provides a head start. Key descriptors include pore size distribution, specific surface area, and surface functional group density. Hydroxyl, carboxyl, and amine groups can chemically bind polysulfides. Random forest regression predicts capacity retention after extended cycling based on carbon host properties. Training data includes different carbon materials with varying pore sizes, surface areas, functional group densities, and sulfur loadings. Feature importance analysis reveals that pore size and functional group density are the most predictive features. Bayesian optimization then searches for the optimal combination of these properties. The optimized carbon host has mesoporous structure with pore sizes ideal for trapping polysulfides while allowing electrolyte access. Appropriate hydroxyl functional group density provides chemical anchoring. Sulfur loading is optimized to balance capacity with host effectiveness. Experimental validation showed excellent initial capacity with high retention, exceeding model predictions. Coulombic efficiency reached practical targets, meeting application requirements. Lithium-sulfur batteries are finding applications where energy density is paramount. Drones benefit from the high specific energy, extending flight times significantly. Electric aviation, including air taxis and small aircraft, needs energy densities that only Li-S can provide at reasonable weight. Prototype lithium-sulfur cells have demonstrated roughly 400 to 500 watt-hours per kilogram, well above today's lithium-ion cells, and sulfur is a cheap and abundant raw material, which is what makes these emerging applications look feasible. Full commercialization awaits further cycle life improvements. Our third case study addresses one of the biggest barriers to electric vehicle adoption: charging time. Using reinforcement learning to optimize charging protocols, researchers achieved the goal of 80% charge in 10 minutes while maintaining battery health. Fast charging faces 3 major challenges. Lithium plating occurs when lithium ions deposit as metal on the anode surface rather than intercalating into graphite, potentially causing internal short circuits. Heat generation accelerates degradation, with high temperatures causing rapid capacity loss. Standard fast charging significantly increases degradation rate. The target is reaching 80% charge in 10 minutes with minimal degradation. Reinforcement learning provides an elegant framework for charging optimization. The state space includes state of charge, terminal voltage, temperature, and internal resistance. The action space is the charging current at each step, ranging from trickle to fast rates. The reward function balances charging speed against degradation penalty. Deep Q networks or actor-critic methods learn optimal policies through simulated charging cycles using pi-ba-mm for physics-accurate battery modeling. The implementation compares 3 charging protocols. Standard constant current constant voltage at 1 C takes about an hour. Simple fast charging at higher C rates reduces time but increases degradation. The ML-optimized protocol uses variable current, starting high when the battery is cold and empty, reducing as it warms, then tapering near full charge to avoid lithium plating. The optimizer learns this strategy automatically by maximizing the speed degradation trade-off. The optimal protocol achieves 80% charge in about 10 minutes. Phase 1 uses high current, taking advantage of the battery's capacity to accept charge when cold and empty. Phase 2 uses moderate current as temperature rises. Phase 3 reduces further. Phase 4 uses low current to avoid the lithium plating risk at high state of charge. Maximum temperature stays well within safe limits. Degradation rate drops dramatically compared to naive fast charging, showing excellent improvement. Stanford researchers validated this approach in a landmark paper published in Nature in 2020, led by Peter Attia. Experimental charging time was about 10 minutes to 80%. After extensive cycling, batteries retained high capacity. This research attracted immediate industry attention and has shaped commercial fast charging development, though the protocols individual manufacturers actually ship are not public. Charging infrastructure is already deploying high-power chargers capable of supporting these fast protocols, enabling significant range recovery in 10 minutes. This work was published by Attia and colleagues in Nature in 2020. Our fourth case study addresses the ethical and economic challenges of cobalt dependency. By using multi-objective optimization to maximize nickel content while maintaining safety, researchers are enabling the transition away from problematic cobalt. Cobalt presents multiple problems. Price volatility impacts battery economics. A majority of supply comes from the Democratic Republic of Congo, with associated geopolitical and ethical concerns, including documented child labor. The alternative strategy increases nickel content for higher capacity while reducing cobalt. The industry has progressed from earlier formulations with higher cobalt to current ones with significantly less, and now targets formulations with minimal cobalt content. High nickel cathodes require balancing competing objectives. Capacity increases with nickel content. Cycle life benefits from cobalt stabilizing effect. Thermal stability, critical for safety, improves with manganese content. We formulate this as multi-objective optimization with weighted objectives for capacity, cycle life, and safety. A hard constraint requires thermal stability above a safety threshold. Multi-fidelity optimization combines ML predictions, DFT calculations, and experiments. The implementation evaluates NCM compositions across the feasible nickel-cobalt space, with manganese making up the balance. Models predict capacity, cycle life, and thermal stability as functions of composition. Compositions violating the thermal stability constraint receive large penalties. Bayesian optimization efficiently explores the Pareto front of optimal trade-offs. Visualization shows the capacity versus cycle life trade-off with compositions colored by nickel content. The optimization identified a high nickel NCM composition as optimal. Predicted and validated performance includes excellent capacity, over 1,000 cycles to 80% retention, and thermal stability above the safety threshold. Compared to baseline formulations, cobalt content dropped significantly, achieving about a 60% reduction. This translates to substantial reduction in material costs while maintaining acceptable safety margins. Industry adoption of high-nickel cathodes is accelerating. High-nickel NCM cells, including NCM 811, are used in some long-range electric vehicles, while lower-cost models have shifted toward lithium iron phosphate. Chinese and Korean cell makers moved ultra-high nickel formulations into volume production through the early 2020s. The key enabling technology is surface coating that protects the inherently less stable high-nickel particles from degradation. Market projections show high-nickel cathodes capturing the majority of EV battery share by 2030, driven by both performance and cost advantages. Our final case study examines sodium-ion batteries, a technology that eliminates lithium entirely. By leveraging transfer learning from lithium-ion research, developers accelerated Na-ion cathode discovery and achieved commercial production in 2023. Sodium-ion batteries offer compelling economics. Sodium is abundant in seawater, eliminating resource scarcity concerns. Raw material costs fall to roughly 60% of lithium-ion, and finished cell costs land at about 70%, matching the range given in Chapter 1. Much of the knowledge developed for lithium-ion systems transfers directly. However, challenges remain. Energy density reaches only about 70% of lithium-ion. The larger sodium-ion slows diffusion compared to lithium. Operating voltage is somewhat lower. Transfer learning dramatically accelerates Na-ion development. We pre-train models on the large database of lithium-ion cathode materials, learning general relationships between structure and performance. Then, we fine-tune on the small dataset of sodium-ion materials. The hypothesis is that materials with similar crystal structure types show similar behavior regardless of the mobile ion. Graph convolutional networks capture this structural similarity. Accuracy improves significantly after transfer learning. The implementation encodes Na-ion materials with structure type O3, P2, or NaSiCon and average voltage. After training on known materials, the model predicts capacity for new compositions. Structure type proves highly predictive. P2 structures generally offer higher capacity than O3. Energy density calculations combine predicted capacity with operating voltage. The model enables rapid screening of candidate materials before expensive synthesis. The transfer learning approach ranked sodium vanadium fluorophosphate, a NaSiCon-structured cathode already well known in the sodium-ion literature, as the strongest candidate in its search space. It delivers about 130 mAh per gram at an average voltage near 3.9 volts, which works out to roughly 160 watt-hours per kilogram at the cell level. Cycle life reaches about 2,000 cycles with high retention. Transfer learning reduced required experiments significantly and compressed development time from years to about 1 year. The approach provides a template for accelerating development of any new battery chemistry. CATL, the world's largest battery manufacturer, announced its first-generation sodium-ion cell in 2021, and Chinese manufacturers moved sodium-ion cells into commercial production from 2023. Primary applications include stationary energy storage, where energy density matters less than cost, and budget electric vehicles for price-sensitive markets. Cell-level cost is significantly lower than lithium-ion. Market forecasts project billions in annual Na-ion battery sales by 2030, with the majority in stationary storage, followed by EVs and industrial applications. Let's compare our 5 case studies. All solid-state batteries use GNN plus Bayesian optimization to significantly reduce experiments, targeting 2027 commercialization. LIES used random forest with substantial experiment reduction to achieve high energy density. Fast charging used reinforcement learning to achieve 10-minute protocols. Cobalt-reduced NCM used multi-objective optimization for significant cobalt reduction. Na-ion used transfer learning with dramatic experiment reduction for cost savings. Each demonstrates the power of matching MI methods to specific challenges. The first best practice is clear problem definition. Quantify your optimization objectives numerically: target capacity, cycle life, cost. Set explicit constraints for safety requirements like thermal stability thresholds and regulatory compliance. Well-defined problems enable appropriate method selection and objective evaluation of solutions. Vague goals lead to vague results. Match your MI method to the problem characteristics. Limited data suggests transfer learning from related domains or Bayesian optimization for sample-efficient search. Structural data, like crystal coordinates, calls for graph neural networks that learn directly from geometry. Time series data like cycling curves suits LSTM or GRU recurrent networks. Control optimization problems benefit from reinforcement learning. There's no universal best method. Context determines the choice. MI works best when tightly integrated with experiments. Active learning efficiently guides which experiments to run next based on model uncertainty. Multi-fidelity approaches combine cheap ML predictions with expensive but accurate DFT and experiments. Early validation through prototype evaluation catches model errors before committing to full-scale development. The goal isn't replacing experiments, but making each experiment count more. Moving from lab to factory introduces new challenges. Scale-up may change optimal parameters due to different mixing, coding, and thermal conditions. Manufacturing process optimization is often more impactful than material optimization. Supply chain establishment ensures reliable access to optimized materials at scale. Safety assessment, including thermal runaway testing and long-term reliability validation, is essential. Regulatory compliance with standards like UL and UN 38-3 must be verified early. Congratulations on completing this 4-chapter series on battery materials informatics. In Chapter 1, you learned battery fundamentals, operating principles, performance metrics, and battery types. In Chapter 2, you mastered ME methods, descriptors, prediction models, degradation forecasting, and optimization. In Chapter 3, you implemented these techniques hands-on with 30 Python code examples. And now in Chapter 4, you've seen how leading companies apply these methods in practice. You're now equipped to apply MI to battery development challenges. Your MI learning journey can continue with our related series on nanomaterials MI fundamentals, drug discovery MI applications, and catalyst MI applications. Key resources include the Materials Project Database, PyBA simulation library, and Battery Data Genome Experimental Data Repository. The AI Terakoya community provides ongoing support and discussion. Thank you for learning with us, and we look forward to seeing how you apply these techniques to advance battery technology.